Okay, so I'm recording today. I'll try to do that for the remainder of the term. Of course, if it means that attendance drops off, then I'll stop doing that. I'm still taking attendance, of course. Okay, Dalton.
Here.
Yeah, Dalton is here. Okay. Eric.
I'm here.
Yep. Caleb.
Here.
Okay, and Brandon, I saw. Kevin.
Who's recording?
Yeah, I'm recording.
Oops. Oh, okay. Thank you.
Yeah. So I'm recording. I assume there's no objections, but I, should ask. So Kevin is here. Did I see Michael? Michael? No, Michael. Okay, Connor.
I'm here.
Okay, thank you. Ricardo's not here yet. Oh, he's here. He's connecting to audio. Davison, I saw Chris is was Chris in the background of one of the cameras? Is Chris here? Okay. Sydney is here. Blake is here. Blake R is here. Joseph's here. Blake S is here. Correct? Both Blakes. Yep. There's Blake S and
Yep, I'm here.
Blake R. Yep. All the Blakes. Dan's here. James is here. Amanda is here. Right. Yep. There she is. Alejandro, are you here, Alejandro? Alejandro. Okay. Nicholas, I think is here, right? Nicholas?
Present.
What's that? Present? Yeah,
Present.
okay. You are present. And Noah's here and Claire is here. So let's see who comes in late. We got to take bets on that. Okay.
You might have called me already, Professor. Sorry, I'm here. How's it going?
Ricardo, yeah, I saw you logging in. And there's Chris. Okay, so Chris is present. Okay, so right now I have Michael and Alejandro as being missing. That seems correct. Okay, still seems correct. Pretty cool. All right. So anybody have any questions on project 4?
Professor, for project 4, do you want us to just multiply pi by 2, like right then and there in the label, or do you want us to do like vector math?
No, you don't have to do vector math. You decide if you can avoid an instruction that way, because there is, if you follow the math in the C code literally, there is a multiplication by 2 there. So if you want, I suppose, well, you do the algebra, and if it makes no difference to pre-multiply by pi by 2, go right ahead. So no vector math, that's actually project 5.
If we're printing garbage, really the only reason that would be is because something's off with our math, right? To get that offset.
Right. So if you're printing garbage, it means you're going outside that array of about 10 characters.
Okay.
Okay. Anybody else have a P4 question? Yeah.
Yeah, related to that. So if we do run into the carrots, should we just basically omit them? We don't want to replace them with anything. We should just go on to the next iteration, essentially.
If you end up with the carrot,
Yes.
yeah, replace the carrot. If you end up with the carrot, then replace it with the, I think the @ sign is the last symbol in the valid symbol.
Yeah.
Yeah. Right.
Okay. Thank you.
Okay. Anybody else? All right, let's take a look at project 5. Project 5 is now online and it is here. So you'll be doing SIMD programming. You're going to learn a couple of things in this. Okay, I got to push a button here, and then I got to do that. And I think I can see everybody. Okay, so there's two things you're going to learn here. One is perhaps your very first introduction to multi-threaded programming. And this is a pretty gentle introduction. There's no synchronization that is required per se. But the other thing is, well, actually two other things. You're going to do vector math, SIMD math, but, so that's one thing you're going to learn. And then the second thing about the SIMD math is you're not going to do it in assembly language. Okay, so this project is 100% C++. Okay, everybody got that? No assembly language. Okay, so you're going to use a neon intrinsic. So an intrinsic is, I've mentioned before in passing, an intrinsic looks like a C or C++ function, but actually it's just a very thin wrapper for an assembly language instruction. Okay, so you're going to write this program that in one program, you're going to implement 4 solutions. Now, I give you the first one, which is just an unrolled loop, adding one vector to another, placing the results in a third. And let me, come on. All right, so here, let me swap to this. Okay, so let's call this A and let's call this B. And you're going to allocate these using a special version of malloc. It has to be an aligned, memory aligned allocation. And it has to be aligned on a 16-byte boundary. And that's because we're going to be using a neon intrinsic that assumes it's work, that does work on 16 bytes at a time. So no matter what length of you're given as a command line argument, you have to make sure that you round upward if necessary to make it a multiple of 16. So if you specify a size of 7, it's got to be 16. If you specify a size of 17, it's got to be 32. Got it, everybody? Okay, so what this is going to do is you're going to fill this in, all of this and all of this, with random numbers between 0 and 1. Okay, so that means on average, the average value will be 0.5. And then you'll take A sub 0 and add it to B sub 0 and put the results in C sub 0. So if this averages out to 0.5 in every cell, and this is on average 0.5 in every cell, then on average, this is going to be 1.0 on in every cell. You got it? Okay. So the you'll also write a function. This is how you're going to check your results to see if your results are correct. You're going to write a function that will add up all the entries in whatever vector you specify. So the very first solution you're going to do is just let's go here. is just going to be that. Okay, so this is a single core solution, and it takes a pointer to the A array and the B array and a pointer to the C array. And it also takes the size. So this assertion here ensures that the size is a multiple of 16. Because if any of the first 4 bits are a 1, it can't be a multiple of 16. Then it reduces the size by dividing it by 16. And that's because there are 16 additions right here. So if the size comes in as 16, this division will result in size being 1. It'll go through this loop once. Okay. So this is, once again, I think we've talked about it. This is called loop unrolling. I remember the last time we talked about it, somebody in class said a professor told you never to do that. And no, it's the right tools for the right job, folks. So here is an application of loop unrolling. It means that the work necessary to do the counter there, the loop counter, is amortized over 16 real pieces of work. That's why it's done. Now, the reason why I did the 16 is because the SIMD instruction is going to work on 4 floats at a time. And you can unroll that loop, which is not shown here. You have to write it. You can unroll that loop 4 times. So 4 times 4 is 16. So it's pretty much apples to apples. Okay. Here is a sample, but let me show you the full program. Okay, we'll get to the threading later. Let me show you the full program. New share terminal. And so let's see. Okay, so G++. Now I'm going to compile it the first time and it's going to fail. Everybody got that? It's going to fail. So main.cpp, and it fails big time. The reason why it failed is because of my use of C++ threading, which was not introduced until C++, hello, not introduced until C++, what is going on here? Okay, standard equals C++ 11. And I don't know where that came from, and the terminal's not responding to me properly. Okay, so now that I told the compiler to use the C++ 11 standard and compiles with no errors. One more thing I'm going to do is, since I know this is working, I'm going to optimize to make it the code run as fast as possible. So you must implement getOpts. Have we done a program with getOpts in this class? Nobody? All right, well, add that to the list. I have a tutorial all ready to go on getOpts, so not a problem. You're going to use getOpts to implement command line arguments. So there's -H, and -H prints this help message. Okay, /a.out. The default values are 128 for the size and 1 for the iteration. So here is a complete run. And it only becomes more interesting once we yeah, my terminal's wacky. All right, I've had enough. I'm starting another terminal. I've had enough. Okay, so it's working nicely now. /a.out -s. Let's make it a bigger array, and then number of iterations 10. Okay, it's cooking, it's cooking, it's cooking. All right, so it's going to report the size, the amount of memory that was allocated, in this case, a little more than a gigabyte. You may not be able to do on your virtual machines. You're going to be limited by the amount of memory in the virtual machine. It's telling me that this processor has 10 cores available. And now here's the unthreaded timing. Notice that the check value, this is how you know you wrote your code correctly. The check value is approximately equal to the size, plus or minus a little bit due to random numbers. But if you recall, it is something that averages around a half, added to something that averages around a half. So on average, it's going to sum to a 1. And therefore, Fredo, I can't keep rubbing your belly. Come on, go. Go away. Come on, go away. So you should come up with an answer that is roughly equal to the size of the array. The next thing that you can use to determine if your code is working correctly, this is just straight C++. You know how to do this. And then here's the answer given to you by summing up the whole vector. This is the C vector. And notice, here's your check. Every one of these is the same. So there's my proof. I take it for granted that I wrote my naive C++ version correctly. And then my single threaded neon produces the same result. My naive with multi-threading produces the same result. And my multi-threaded SIMD neon produces the same result. If you get any different values there, you know you have a bug. Okay, everybody got that? Okay, so what are we looking at here? So a single core version, it written in C++ with loop unrolling, so it's not quite that naive. Took 0.035 seconds. But then if you look at the neon, also single threaded, it's approximately twice as fast. But then if you look at multi-threaded, the naive version is now about 3 times faster, even with 10 cores. It's only about 3 times faster. We're going to learn about that today. You might think it was going to be 10 times faster with 10 cores, but you'd be wrong. And now the neon version is about, I don't know, about 7 times faster than the original. Okay. If you go too big, you should print a message saying memory allocation failed. I could not allocate that many. Now, something else I want you to notice, that if the size is small, check this out. the multi-threaded versions actually took a lot longer than the single-threaded versions. Now, we don't really know what threading is yet, but why do you think that might be? We'll revisit this if we have to.
I guess there's probably some overhead involved because, you know, you're doing something beyond just doing the math. So there might be some amount of overhead in setting that up.
That's correct. So the reason why the multi-threaded versions take longer than the single-threaded is that the amount of work I'm asking each thread to do is so small that the timing is dominated by just setting up the threads. But once we make a bigger, so here's the default value of 128, and still too small to see anything. Here's 1024, 1024, just a random number. I'll do it with one iteration. So once the amount of work each thread is doing becomes large, then it starts showing performance benefits over the single threaded. So let's do a really big one here. So this one's big. This one is really, really big. The single core versions are taking forever. So this is 11 gigabytes of memory. And take a look at how much faster the Neon multi-threaded is from Naive. This is on the order of 35 times faster. Okay. Once again, I look at my check values and I see they're all the same. Okay. So let's, do you have any questions about the project?
Kind of tangential, but is there a reason that G++ by default is using such an old C++ standard to compile that we have to explicitly say use C++11?
Historical legacy reasons, right? Because by default, it's going to compile with the original version of, essentially the original version of C++. So anything newer is a command line option. Okay, all right. So anyway, let me come back here before we leave the, what can you see right now? You should be seeing the Safari. Okay. So SIMD means single instruction, multiple data. And ARM offers the Neon instruction set, but there's also another instruction set that is even more sophisticated, but I'm not teaching you that. The ARM is, the Neon is pretty cool by itself, although it's not the be all and end all of SIMD instructions. The main difference is that Neon instructions are designed to work on a specific number of arguments. So for example, the Neon instruction that you're going to use is VADDQ_F32. That is designed to work on 4 floats of A and 4 floats of B, adding them together, putting them into the result into 4 floats of C. Now, the newer SIMD instruction set, what separates it from Neon is that one, it will continue streaming through memory as far as you tell it to go. So instead of an instruction that works on 4 at a time, you can say, here, work on 1,000,000 at a time. And it will just keep running until it does all 1,000,000 in an optimal manner. Okay? So the newest SIMD instruction set on ARM is a streaming instruction set. So you're going to write a version of something similar, but it has the same signature as single core, but it's going to use the intrinsic. So pointer to A, pointer to B, pointer to C, and a size. Okay. All right. So any questions about the intrinsic? You will have to look it up and figure out how to use it. Okay. One thing I will tell you right away is that notice there are new types like int 8x8 underscore t. Well, let's go find. So here's the one that you'll be using, float 32. So each of the 4 arguments is a normal float, and there are 4 of them. Oh, look, and there's the actual, I happen to land right on the one that we're using. Okay. All right. Now, let's talk about yes, Noah, it's basically a library of functions that are wrappers for fancy instructions in the assembly language. So that way it looks like you're writing C and C++, and you are, but there's a very fast path down to the assembly language.
And it's for neon instructions specifically.
Yes, it is. Yeah, so you wouldn't be able to use these intrinsics on an x86, for example. They have their own. Let's go back to here and scroll. There's quite a few includes for you to use. And I've listed them here. And here's where you get your intrinsics from. So everybody see the include of arm underscore neon.h? If you write this code on your Windows or Mac, it's not going to have that include file. You're going to get a red squiggly in Visual Studio Code or Xcode or Visual Studio. Don't worry about it. Once you squirt it over to your ARM virtual machine, it'll work just fine. Okay. This, I think, is true on Linux, but it's not true on the Macintosh. If you look at the recording, you'll notice I did not specify it, but I think that's a Macintoshism. All right, is there anything else?
So you mentioned recording. I noticed that this lecture is getting recorded. Was that by you?
Yeah, by me.
All right, excellent.
Okay, and once the class is done, I'll start a YouTube channel playlist for this class. Okay? Noah approves. I feel validated.
Man, up until this point, it was just hard sailing.
Okay. All right, now let's take a look at the mechanics of C++ threading, and it's only in C++ 11 or later. And then we're going to look at what threads are, and we're going to look at why, if you have 10 cores or 10 threads, why isn't it 10 times faster? Okay. All right. So here is an example. The link is to c++.com. And here is a link to the page describing std::thread. And I link that from the project, and I'm repeating their example here. So C++11 and later has a type called a thread. It's a class. When you create it, you are, this is one way of creating and spawning threads. Here I'm saying the first thread is going to execute foo. Okay, no arguments. Let's take a look at foo. Thread, the thread entry points are all voids. They're all void functions. In this case, I said no arguments here. And look, there's no arguments there. In second, all I did was specify an integer argument, and that sets me up to have a thread which accepts an integer. And this is way, way, way simpler than the package called pthreads, which is what this is based on. Pthreads, or POSIX threads, was the first threading library. It came out in Berkeley Unix, in Berkeley, I don't know, Berkeley 4.2 or something like that. And in order to send arguments to the thread, all you got was one void star. So if you wanted to send multiple arguments to a thread, you'd have to put them in a struct and then cast the type of, give a pointer to the struct, casting it to a void star, and then uncast it inside the thread. And it was a kind of a pain, but it was certainly understandable, certainly doable. But C++ threads make it trivial to pass arguments to a thread. All you got to do is match whatever, however you called created the thread instance. Then after the threads complete, the main thread will wait for the completion of the threads by calling join. So this is a trivial, like hello world example of using C++ threads. Use this function to find out how many cores you have. Your ARM VM alias has 2 cores. So if you want, you could change your alias to have more cores just to play around with it. And that is, where do I talk about the SMP? Okay, yeah. So your ARM virtual machines are started by this, and this is the part that controls the number of cores. -SMP space and a number. So right now it's at 2. If you want to try this with 4 cores or 4 simulated cores, then change that to a 4. Anybody have any questions?
Are these cores,
yeah.
so like, you know, hardware, you know, CPUs can do some weird stuff. So like one physical core can run 2 threads at a time. Knock on wood, it's like, are these 2 cores that each run 1 thread at a time, or do they
Yeah, that's only an Intelism. So on the ARM, 1 core runs 1 thread at a time. Now, you can create on a single core processor, you can have 1,000 threads. It's just not, only one of them is going to run at a time. Okay.
Okay.
Here's how you can do your timing. I've shown you code in the previous class, I believe, of manipulating time vals. But here's one way of getting a timing. You get the time at the beginning, you do your thing, and then you get the time at the end. And you can use timer sub to subtract the end time from the start time, or the other way around. Okay. All right. So let's switch over to the iPad and talk about why it is you know, if you have a gazillion cores, why don't you get a speed up of a gazillion? Okay, and that's Amdahl's law. So here's a picture of Gene Amdahl. You'll find this picture on his Wikipedia page, and you'll note that the photographer, the person who took that picture, was me. So, gee, I'm famous. I'm on Wikipedia because I took Gene Amdahl's picture. He passed away in 2015 in his 90s. He was a 1952 PhD in electrical engineering at UW-Madison. And he designed one of the earliest computers, which Madison built after he left. It was called the WISC, W-I-S-C. And today, the WISC is in a warehouse at the Computer History Museum in Silicon Valley. And it used to be on display, but you know, they did some shuffling of the exhibits. When it was on display, people would marvel at the fact that it had bullet holes in it. So if you think you ever get mad at your computer, no, that's not quite right. When the last person who knew how to work the WISC retired from UW, he asked for permission to take it home. And they said yes. So the gentleman had a construction crew cut a hole in his foundation. And with a crane, they hoisted it into his basement and then sealed up the foundation behind it. And then he continued using it. When he passed away, his son had no freaking idea what to do with it. So what do people in Wisconsin do? You know, it's coming to hunting season, so he tested out his weapons on this priceless computer science artifact. And that's why there are bullet holes in the WISC. Darn this thing, I gotta change the timeout. Okay, so one of the things that Amdahl did is actually he founded a company called Amdahl, and they were the first clone makers. They didn't clone IBM PCs, they cloned IBM mainframes, which is pretty interesting. But he also did a bit of theory, and he created Amdahl's law. The formula is here. And what it does is it will tell you the maximum amount of speed up that you can get out of parallelizing your code. All right, and the input is P and S. So P is the fraction. Now, the way it's documented is kind of misleading. It's the fraction of code that can be run in parallel. Now, that's misleading because how do you measure that? Is it the number of lines of code that can be run in parallel? That would be silly. So really, you should think of it as the amount of work. So P represents the amount of work that you can run in parallel. So 1 minus P represents the amount of work that's going to run serially that you can't make into parallel using threads, for example. And then S is the number of times, think of it at that as the number of threads. Okay? So think about P in terms of the amount of work. What is the fraction of work that you can parallelize? And then S is how much you could speed up just that portion. So check this out. Let's say the amount of work that you can parallelize is only 30%. So, okay, let's try with 2 cores. Well, your speed up is only going to be 1.18 times. No problem. Let's add 20 cores. Well, 20 cores, we're only 1.4 times as fast. Hey, no problem. Let's add 2,000 cores. Wow, we get up all the way to 1.43. So Amdahl's law shows us that the amount of speed up from multiple threads is entirely dependent upon what fraction of the work you can speed up by having multiple threads. And in fact, having an infinite number of cores doesn't do you any good. Okay, so diminishing returns, diminishing gains. Now take a look at the next example, where 70% of the work can be made to run in multiple threads. All right, so with 2 cores, I get 1.54. With 20 cores, I'm up to triple the performance. 200 cores, I'm up to a little more than triple the performance. 2,000 cores, and I peaked out at around 3.33. So the returns of making parallel programming always flattens out. Okay. All right. Now, this is a theoretical tool. And really what he was talking about is the amount of work that can be parallelized. So for instance, in project 5, the work is just doing the summation of the vectors. But in modern programming, once again, we can't make our cores go faster, but what we can do is add more cores. Because core speed translates into heat. And there are thermal barriers after which the silicon fails. So we can't increase the speed very much of individual cores, but certainly we keep shrinking the cores so we have room to add more of them. Now, Amdahl's idea of multi-threading was, I guess the right word is homogeneous. So all of the work was the same, homogeneous. But in modern programming, you use different threads for different purposes. So for example, in a video editing product, you can have one thread just spooling in, reading all the video data, and another thread displaying it, right? So that the I/O is being done in parallel with the processing. So that's not exactly what Amdahl was thinking about, all right? Does anybody have any questions about what I've said so far about threading?
Yeah, I have a question about
Go ahead,
like
Nicholas.
the diminishing returns on the cores. So does that mean that like if I want to get the new Apple M1 Pro chip with like 32 cores, that it really is just a waste of money, that I should just stick with the 16 cores?
No, not necessarily. And that's the answer is exactly the subject that I was just talking about, which is Amdahl was thinking about all cores doing the same thing. But on a modern computer, you might have one of your cores running Word and one of your cores running YouTube and one of your cores running something else. So yes, for generic computer usage, the more cores you have, the happier you are.
Gotcha.
Okay, so yes, one more time, Amdahl's law really applies only to just a very homogeneous set of code, whereas modern programming requires that students understand how to write multi-threaded programming. The future is multi-threaded. If you graduate college without knowing how to write threaded code, then you had a crappy college education. Okay? All right. So anybody have any questions on the theory of the speed up or project 5? Okay, so let's take a peek at how threads are made. And by made, I mean actually made. Not C++. I'm talking about way down deep inside the operating system. So we've seen, this time I'm going to draw it big. We've seen pictures like this. Oh, how many times? So many times. Okay. Now, in addition to this diagram of a virtual address space, there is inside the operating system some table that contains metadata about your process. Let me see the chat. If multi-threaded is the future, why is JavaScript single-threaded? Well, is that completely true all the time? There's no way to get more than one thread out of JavaScript? If that is, I don't think that's the case, but if it is the case, that's a browser problem. Okay. Okay, so there's some metadata that keeps track of information about your process. Now, one of the things that it has is a pointer to your page table, and we've discussed the page table before. So the page table is what is actually implementing your virtual address space, right? This is the way that the page table defines where your pages actually are, either in physical memory or on the swap device. Does everybody recall that discussion? Okay, good, because I'd hate to do a refresher on that, because it takes a while. So in order to implement a thread is an executing process, right? So what do you think we need to do to the virtual address space in order to implement threads? Should we duplicate it? Well, if we duplicate it, then it's kind of like having a separate process, right? If it's duplicated, then the virtual address spaces are not the same. But that's the defining characteristic of threads. Threads share address spaces. So my question comes back to you once more. What do we need to do to this in order to support multiple executing units in the same address space? Should we duplicate the code area, or can they all share the code? Hello? Do I have to change the code area at all?
I don't think you will.
Yes, is something in the wrong order in the model that you made there?
What? Was that Noah?
No, never mind on what I said.
Yeah, these diagrams are traditionally drawn upside down. So zeros at the top. Okay. All right, so we don't need to change anything in the code area. Does each thread need its own heap?
I don't think it does.
Nope, nope. The heap stays the same. Does each thread need its own stack?
I think I could probably share that too.
Well, isn't it the stack that really defines where your code is executing? Right? I mean, go away, Fredo. Puppies don't take this class. All right. So what every thread requires is its own stack, because as thread 1 is calling one function, that goes on a stack. Thread 2 is maybe calling a different function. That's going to go on a stack. It has to go on its own stack. So here's how the operating system creates threads. And one of these years in the OS class, I'll actually assign this as a project. I haven't had the nerve to do it, but it's fun. It's so satisfying when you succeed. So here's how making a new thread works. We'll take this giant virtual address space and we will divide it and say this is the stack for thread 2 and this is the stack for thread 1. So this one can now grow this way. This one can now grow this way. And of course, the heap can grow that way. Now, you might say, but wait, doesn't that divide the virtual address space, putting a limit on the amount of heap growth, the amount of stack growth? The answer is yes, it does. However, on a 64-bit machine, we're talking about a virtual address space, which is freaking enormous. So yeah, it's dividing it up, but it's practically like saying half of infinity. Okay, you only get 1/3 of an infinite number of dollars. Oh, gee, that's too bad. Okay. So 64-bit machines is it's virtually unlimited address space. Who cares? Now, that's not the end of the story. So I told you that there's some place that has metadata about the process. Another, for every thread, another set of metadata is created, but the metadata is going to point to the same address page table. Each of these are pointing to the same page table. presto changeo, you're sharing an address space. So you might look at this and say, oh, that's one process and that's one process, and they're separate processes, but no, they are marked as threads versus processes. They are marked that way, but the defining characteristic is they point to the same page table. And because of that, they share the same address space. Okay? All right. So one more compare and contrast. Having multiple programs, a picture I like to draw, is like having multiple apartments or multiple dwellings. Okay, so this virtual address space is completely separate from this virtual address space. And they can't share unless you do some trickery, like sharing data via a pipe, sharing data via a file, sharing data via specially created shared memory. Okay, but let's compare this to multi-threaded program. That is like having roommates in the same dwelling. So you're sharing one virtual address space, and therefore every roommate has access to the memory of all the other roommates. For example, maybe here is the heap. All of the roommates have access to the heap. And that's wonderful. That makes things really fast for communicating between the threads. But of course, nothing is free in life. That comes with its own problems. And part of this course will be learning about the problems and how to avoid them. Okay, anybody have any questions? All right. Only a handful of people have turned in project 4. You've got some grace time. Now, in order to give you a bit of an opportunity to catch up if you are behind, instead of 7 days, I made project 5 9 days, so that you have a little bit of an opportunity to work on any missing work that you have. Okay? Please do not overthink project 5. Let's see. Web workers. Okay, yep. I think that is threading. All right, now the defining characteristic of multi-threading, as Dan's saying, that sounds more like multi-processing versus multi-threading. The defining characteristic of multi-threading as compared to multi-processing is, do the executing agents share the same address space? Those are threads, or do they have separate address spaces? Those are multiple processes. Okay, so recall that I mentioned that threading was only introduced in Berkeley like 4.2, maybe it was 4.1. So we're looking at the early 80s when threading was added to Unix. And before that, you could do multi-processing. Used to write multi-process systems all the time using pipes or files. AT&T went a different way. They added shared memory. In today's Linux, you have both threading and shared memory because today's Linux is just basically it's a vomited up dog's breakfast of everything that anybody has ever thought of, which is not at all what Unix was supposed to be. Okay. All right, once again, anybody have any questions?
Just out of curiosity, so we're writing, you know, this ARM code that runs on a virtual machine, so it has to get translated to our presumably x86 CPUs. Are these neon instructions getting translated to the appropriate SSC instructions for our CPUs, or are we just emulating what would be such a slow ARM CPU that even that we can effectively get the neon speed-ish from just running it single threaded on a x86 core?
Yes, you're running on an emulator. The virtual machine is emulating the ARM hardware in software. So yes, you're running on a really slow ARM. For Project 5, don't make really big buffers. It's going to take forever. Okay. But you will see performance differences. Now I'm running, I gave my demo on an ARM-based Mac. And one of the virtues of C++ threading is, and the intrinsics is that code that I wrote, my version of the project, runs without change on the Mac and on Linux. But that wasn't your question. The answer to your question is, yeah, you're gonna be running on a really slow ARM. Emulation can be pretty cool. I mean, you take one of your Windows machines and have it emulate an Atari 5200, and you'll have a really fast Atari 5200. Even though it's emulated in software. It's actually faster than the hardware was. Okay, other questions? Okay, so I hope that you find P5 a nice break from coding in assembly language. It'll give you some opportunities to learn more things about C++. And with that said, we can draw this class to an end, and I'll, once the recording is available, I'll put it up to the cloud. Okay, everybody, I'll see you on Wednesday.
Thank you, Professor.
Thank you.
Thank you. Goodbye.
Thank you.
Bye-bye, thank you.